Okay, welcome to today's YouTube lecture. We're going to be discussing Newton's three laws of motion. Before we proceed, please make sure that you're taking your Cornell notes. There is nothing on my class jump page that will help you this time. You should have notebook paper out. It should be set up in Cornell style. Remember to take the body of your notes first, go back and establish your essential questions, and then do your conclusion in the end. So, Sir Isaac Newton, born 1642, passed away 1727. He developed his three laws of motion by the age of 24. His first law is called the law of inertia. The second law explains the relationship between force, mass, and acceleration of an object. And the third law is known as the action-reaction. Newton's laws proved to be more correct than Aristotle's ideas of natural and violent motion. So he took the philosophies and ideas from previous scientists and philosophers and expanded on them. And these are laws, so they're proven to be true. The first law is the law of inertia. Newton's first law is it concerns inertia, and inertia is the tendency of an object to resist change to its motions. The law is exactly stated as an object at rest or in motion will remain at rest or in motion unless it is acted upon by an outside force. Simply put, things tend to keep doing what they were already doing. If you have a pencil on your desk, your pencil will always stay on your desk until someone flicks it and knocks it off the desk, or you hit it with a book and it starts rolling. Imagine driving in a vehicle, and say one of your parents is driving, or maybe an older sibling, and they're not paying attention, or all of a sudden they have to stop. Maybe the car in front of them slams on the brake. So your parent is slamming on the brake, and even though the car stops, your body keeps going forward. Your body has inertia, and it's going to keep moving forward until your seatbelt or your restraining device, your seatbelt, pushes you back into the chair. That tendency to keep moving forward is Newton's first law of motion. And if the seatbelt had not exerted a force on your body, then you would have kept going forward until you hit something else. So the whole idea of inertia is that the greater the mass of an object, the greater the inertia. So if you have a tennis ball or a bowling ball, the bowling ball obviously has more mass than the tennis ball, so the bowling ball has more inertia, and it will take more force to set the bowling ball in motion or to slow it down or speed it up or stop the motion than for a tennis ball. So you would never want to attempt to use a tennis ball to go bowling or a bowling ball to play tennis. Newton's second law of motion. Newton realized that acceleration depended not only on the push or pull applied, but also the mass of the object. Therefore, he proposed his second law, which states, acceleration applied to an object will change, a force applied to an object will change the acceleration of the object in the direction of the force. The equation that applies to this law is force equals mass times acceleration. Now down here we have our triangle. Notice that we have force and mass and acceleration. It's a three-part formula, okay? Force equals mass times acceleration, so you can use the triangle to manipulate this formula if you need to. We measure force in what we call newtons. Basically, mass is measured in kilograms, and acceleration is meters per second squared. So the scientific or the SI unit for force is a kilogram times mass per second squared. That's really long to work with. It's pretty long unit of measure to work with, so we abbreviate it as a newton. And the symbol for Newton is a capital N, and it's named after Sir Isaac Newton. Okay, so here's a practice problem for you guys. An airplane needs to accelerate at 5 meters per second squared to reach takeoff speed before reaching the end of the runway. The mass of the airplane is 5,000 kilograms. How much force is needed from the engine? Now, I'd like for you to pause the video right now and in your notes copy the problem and then tell me what you know, what you need to find, what will the equation look like, and what is the unit for force. Okay, so what do we know? Our word problem is giving us the acceleration. So we know acceleration, if I can get this to move. Yay. And it also gives us the mass of the airplane of 5,000 kilograms. So we also know mass. Okay, what do you need to find? How much force is needed from the engine? So we're looking for force. What will the equation look like? Okay, we have three options down here. We have mass equals force divided by acceleration equals force divided by mass, or force equals mass times acceleration. We're trying to find force, so we need this equation. And then what is our unit for force? It is the Newton. Okay, so check the answers in your notes to make sure they match what's on the video. Let's talk about net force. You have balanced and unbalanced forces. If your two forces are balanced, such as these two, your net force is 0. Okay? That means there is no motion whatsoever. When you have opposing forces, forces moving in the opposite direction, and your arrows indicate the direction, this is a force moving to the right, this is a force moving to the left, they are equal or balanced forces. This force is 15 newtons, this force is 15 newtons. This turns into a subtraction problem because they're in opposite directions. And so they're both acting on this object. However, there's no motion of the object since they're equal, and our net force is 0. Now, if we were to change these forces, and say we have unbalanced forces. So right now, I have 15 newtons of force acting to the right and 5 newtons of force acting to the left. My net force is going to be the difference between these two and in the direction of motion. Direction of motion is the direction of the greater force. So my net force for this problem is 10 newtons to the right. The motion of the object will be in the direction of the greater force, and then the amount of force will be the difference between the two values. If we were to change this and say decided now we had 20 newtons of force acting to the left and 15 newtons of force acting to the right, pause the video and tell me in your notes what direction the net force is and with what value. And what you should have is 5 newtons to the left. Okay. Now, Newton's second law also has taken into consideration free fall. Galileo was the first to show equal accelerations for unequal masses, but he couldn't explain it. By applying Newton's second law, we can prove that acceleration of all objects in free fall is the same regardless of their mass. So regardless of mass, all objects fall at the rate of what we call the gravitational constant, which is 9.8 meters per second squared. So when we're dealing with mass and weight, we've massed objects in class before. Mass has the, since all mass has the same acceleration rate, 9.8 meters per second squared, and Newton's law states that force equals mass times acceleration, then when we're calculating the weight of an object on Earth, it's the object's weight times 9.8 meters per second squared. So for every kilogram of mass an object has, it will have a weight of 9.8 newtons. This is only on Earth because 9.8 meters per second squared is our gravitational constant. If you were on the moon, your mass would be the same, but your weight would be different because gravity is different on the moon than on Earth. Please remember that mass and weight are not proportional, they are proportional to each other, but they are not the same. Mass is the amount of matter. Weight is the mass of an object as gravity is acting on it. So Newton's third law of motion. Newton's third law of motion states for every action, there's an equal and opposite reaction. Some examples of Newton's third law of motion would be a squid swimming. As it's pushing the water behind it, it's propelling forward. Blowing up a balloon and letting it go, as the air is released from behind the balloon goes forward. You swimming, as you're swimming, you're pushing water behind you, propelling you forward. A submarine, the same premise as you swimming or a squid propelling through water. Other examples of Newton's third law of motion would be if two ice skaters are skating towards one another and they slam into each other and then both fall backwards. That would be opposite and equal, okay? Guys, at this point, you need to make sure you get your essential questions. You need to make sure you have a summary. These notes are going to be very important because when we use them in class, you will be doing a quiz on the ActiVote where you are going to be given some questions, and then you will have to answer them and identify the situation as Newton's first, second, or third law of motion. Have a great weekend, and I'll see you guys Monday.